Chapter 16, Properties of Solutions. We're going to look at making solutions. Whether the solute and the solvent are polar, nonpolar, or ionic determines how much will dissolve. So if we look here, we have salt and water. Salt is ionic and water is polar, of course. That will dissolve. Water is polar. Oil is nonpolar, it will not dissolve. It also determines whether a substance will dissolve. So making solutions. A substance will dissolve faster if it is stirred or shaken. That makes sense. You know, if you add a tablespoon of sugar to your morning latte, you don't just leave it there, you stir it there so it goes into solution faster. The thing is, in order to dissolve, the solvent molecules must touch the solute. That's why you stir it, so more of the solvent molecules touch the solute. So the solvent molecules hold on to and surround the solute, just like all you guys, if you see Cody from Heartbeat Boys, y'all will surround him and rip him from the rest of the group. Stirring will just push more of the girls into the teen idols. Stirring will move fresh solvent next to the solute, dissolving it faster. A substance will dissolve faster if the particles are made smaller. That makes sense, of course. If you just put a sugar cube into your coffee, it's not going to dissolve as fast as if you just put a whole bunch of grains of sugar. Particle size, the whole point is a solvent touches the surface of the solute. If there's more surface, like with little grains, there's a lot more surface there, whereas with just a cube, there aren't as many surfaces. Smaller pieces will increase the amount of surface of the solute. Solvent and solute touch each other more often. Smaller particles will dissolve faster. Also, temperature is increased, the substance will dissolve faster. Higher temperatures will make the molecules of the solvent move faster. Higher kinetic energy, more kinetic energy. If they're moving faster, they're going to have contact with the solute more often. If you want to dissolve something, then heat it up. We'll go into solution much quicker. How much? Well, dissolved particles are surrounded by solvent particles. Eventually, the solvent particles are all occupied. There's going to be a limit to how much solute we can put in there. Just like if we had all the teen idols in the world, let's say we had Heartbeat Boys, Varsity Fan Club, Jake Don Wale, Brock Storm, all those guys, we brought them into the room. So right there's 12 guys. And let's say there's only half the class, there are 6 students. Well, pretty soon, if the students are the solvent, you're not going to be able to get with every single guy, or as far as, talk to them. What happens, the solute will begin turning back into solid. It won't be dissolved if there's too much solute. Equilibrium will be reached where dissolved particles are turning to solid as fast as solid is being dissolved. And you can try this. You can just keep adding sugar to a glass and stir it. At one point, if you add too much sugar, it's not going to dissolve. It's going to go back to solid. And you're just going to be adding, no matter what, you just can stir it and shake it. No more will dissolve. The terms we need to look at: solubility, the maximum amount of substance that will dissolve at that temperature. For instance, if we have room temperature, there's only a certain amount of sugar we can add to a glass of water. It's only going to be so much of that sugar will be soluble. Unsaturated can dissolve more solute. If it's saturated, that's it. No mas. It has the max amount of solid that can be dissolved. Once it's saturated, that's as much sugar as in there. We put any more sugar in there, we put any more of that Kool-Aid in there, it's not going to do anything. Supersaturated is oversaturated, and you can get to supersaturated by heating. So we can heat something and cause it. Just a second, my secretary needs to get that. Yeah, I'll just call him back later, thank you. All right, so you can oversaturate something where a solute, such as your Kool-Aid, can be dissolved even more than normal, and usually you can do that by heating. How about a liquid and a liquid? We're just talking about solids and liquids. Well, liquids, we have to look at the term miscible. So if things are miscible, the two liquids can dissolve in each other. For example, acetone and water are miscible. They are dissolved within each other. They are both polar, and so they will dissolve. Whereas immiscible, they can't. They will not dissolve, such as water and methylene or water and oil. Those will not dissolve in each other, so we can see that. Pretty neat. Now this is looking at the particle level. They just won't mix. It's like if we have Sacred Heart and Marion, they're not going to even look at it. Just don't mix. But if we have maybe Sacred Heart, the upper school and the Kensington Hall guys getting together for a dance, or maybe an EC party, they'll join along. They'll mix, socialize, etc. What affects solubility? For solids and liquids, as the temperature goes up, the solubility goes up usually. For gases, though, other way around. If the temperature goes up, the solubility goes down. You don't have things as soluble. Things won't dissolve as well. And you get something, for example, called thermal pollution. So this is a big problem. This is a power plant in the San Francisco Bay Area. It's huge. And what they do is they dump hot water into the bay. And you might think, well, hot water, so what? It's just kind of warming up the bay. The bay is always very cold, and so you warm a little water. But the problem is oxygen, dissolved oxygen in the bay, and this happens all over the place. In fact, you guys might remember from the Tri-Lakes experiment in SciLit, or skillet for short. If you're cool, you usually call it that. They had the same problem, the Tri-Lakes. And this is a problem all over, but the dissolved oxygen, if you put the heat up, the oxygen won't be as dissolved. You won't have as high as a concentration. The concentration, solubility of oxygen will go way down. And what happens, again, the poor little fishies are not going to be able to get that oxygen from the water. A lot of the marine life will die. A lot of the smaller animals will die. You get overgrown of algae, so you get some pollution due just to the heating of the water. And often fish, if you have a tropical fish, they like it a little colder. You don't really want to give them nice warm water like we have, because the oxygen won't be as dissolved in there because it's not as soluble. For gases in a liquid, as the partial pressure goes up, the solubility goes up. If we increase that pressure, we can have more solubility. For instance, CO2 in cola or soda or pop. This is how carbon dioxide stays in your cola can or pop can, as people out here call it. I called my dad pop. But anyway, what they do is, under extreme high pressure, we have a lot of pressure in here, much higher than atmospheric pressure. We put all this pressure in there. That increases the solubility of carbon dioxide. So the carbon dioxide is soluble in that can, and it's able to dissolve in there. Now, what happens when we open that can? The pressure goes way down because it becomes equalized. It's equalized with the outdoor pressure, or the outside pressure. That pressure is released once we open that can. We have low pressure here relative. Inside we have high pressure. And that allows the solubility of carbon dioxide. It allows it to be dissolved in solution. Once that pressure is gone, the CO2 bubbles come out of solution. That's why we get that fizz that makes drinking cola so enjoyable. And that's why cola goes flat after a while, because now all the pressure's gone and the carbon dioxide leaves. It's not, if we can keep the pressure on it, then it would stay fizzy. Now let's look at an example as when gas pressure goes down, the solubility goes down. An example of this would be diving with the scuba tank. So if we think about when we're diving, we have air pressure on top. So at 1 atmosphere or 0.9 atmosphere, really at the surface of an ocean. But then you have all these layers of water on top of you. And that's a lot of air pressure. That's a lot of pressure on top of you. Now, as you scuba dive, you're going to need, of course, to have a tank of air. Now, the air that we breathe is actually 79% nitrogen. Only 21% or less, there's some trace gases in there. 21% is oxygen. We cannot breathe pure oxygen, 100% oxygen, for a long period of time. Because if we do it for more than a couple of weeks or so, or possibly even more than a few days, we'll get all sorts of fluid problems in our body. So we don't want to breathe pure oxygen. So the tanks in our in the scuba gear that we have, or any sort of artificial air that we breathe, usually has about 80–79% nitrogen. But that's a problem, and that causes a problem called decompression sickness if we don't follow the correct procedure of coming back up. So now decompression sickness, also called the bends, caused by breathing nitrogen from the air tank under pressure, which is not metabolized in the body. So we do not metabolize N2. So we have mostly nitrogen in here. Now as we go down, the more pressure, nitrogen will become soluble. So that's actually, as pressure goes up, solubility goes up. We're going to have a lot of nitrogen in our bodies because we're under a lot of pressure here. We have high pressure at the bottom here. So the nitrogen from the gas tank or the air tank will be much more soluble. Our blood will contain a lot more nitrogen than it's really used to. But the problem is rising. If you rise too fast, what happens when we rise, that nitrogen, which is in your body now, it starts to expand. It expands the same way as a pop bottle, or I'm saying pop now, as a cola bottle. Okay, like when you open up a cola bottle, all that gas comes out. It's the same thing with nitrogen as you go up. As you go up to the surface, the nitrogen does the same thing like carbon dioxide bubbles in cola. Nitrogen does that in your blood and causes breathing problems, causes all sorts of pain. The blood doesn't, it has all that nitrogen. So what you have to do is slowly and gradually go up. You decompress very gradually, because as that gas, as it goes up and the pressure goes up, the solubility goes down. The nitrogen is not soluble in your blood anymore, and it just can cause a lot of problems. This leads us into Henry's law, which states at a given temperature, the solubility of a gas in a liquid is directly proportional to the pressure of the gas above a liquid. So we have the basic equation here, S1 over P1 equals S2 over P2. And really, we're just going to solve, we can just solve for any one of these. We can solve for the solubility, we can solve for the pressure. It's just a simple algebra. If we're solving for S2, we'll do that. So let's look at this problem here. It says if the solubility of a gas in water is 4 grams per liter at 2 atmosphere, what is its solubility at 1 atmosphere? So we just have a simple algebra problem here. S1 is 4 grams per liter. S2 we want to know. P1, 2 atmosphere. P2, 1 atmosphere. We put that together and we get 2 grams per liter.